Yeah, all right. So the first thing that I want to do, and this is particularly applicable to the work that we're going to do today, I want to just talk through some things that you can think about with the work that we do in this class, because sometimes the things that we do are going to kind of be, you can kind of think of them as a task, something to do and get checked off, and then you're done. And the quality of the task might be important or might really not be that important. Other things that we do in the class, like the work that we're going to do today, is really not a task. It's not a task. It's an opportunity to practice some skills. So I'm going to talk about that really briefly. This will get posted on Canvas as a video and in a presentation form, so you'll have access to this down the road. So when we talk about a task is something that can be accomplished. You can cross it off a list or check it off. It's done. Once you have done it, your work is done. And sometimes many of you are, go ahead, don't worry about it. Many of you are sort of perfectionists. And so for you, getting a task done, it needs to be done right. It needs to be finished. It needs to be correct. It needs to look good. Like all of those things need to happen. But actually, that's not always the case. Like in some cases, accomplishing a task doesn't need to necessarily look good. So, for example, at the end of the school year, I need to make sure that that everything is off of the desks and tables that could be moved, because they move them around and then they wax the floors and stuff. But I can just put them on the back lab benches. Those can't move. So I just put whatever I want on the sides of the benches. My room doesn't look great at the end of the summer, but the custodians and the district maintenance people can get their jobs done. And then when school starts, I just come and I move everything back, and I'm happy and everybody else is happy. It's not pretty, but it accomplishes the goal of clearing my room so that somebody else can do some work. Other times, the quality of the task really matters. If you, for example, have a job outside of school, I know one of my former students, oh no, you're good, always. One of my former students started a car detailing company. I had him come in and detail one of my vehicles years ago. Really nice guy. And you better believe that the quality of that task matters. If you run a car detailing outfit and you don't do a great job, then you're not going to get a whole lot of referrals. He did a great job, by the way. His name's Spencer. Really good. When we think about tasks, the amount of time that you spend on it can vary, both for you and for the people around you. So for example, if we have a task in this class, if I were to say to you, hey, I want everybody to sign into Canvas, pull up the assignment, fill out whatever for question number 1, and then submit it, you'll notice that as you are progressing, other people are finishing before you or after you, and somebody finishes first and somebody finishes last, and then when you're done, it's like, well, what do you do when you're done? If you're doing a task and you want to check with somebody, a teacher or a supervisor or a friend or whatever, you ask things like, well, am I done? You show them, is this good? Am I done? Did I finish it? Is the work that I did of a good enough quality that I don't need to continue working or do it again? The idea is to get something completed. And you might be the kind of person or be in a situation where then there's something next. What do I do next? What do I work on next? Or maybe you're just like, okay, well, if I'm done, I had this task, you gave me a task to do, now I'm done. Can I read or can I watch YouTube or whatever? And those are all very appropriate things when you're performing a task. If this were a photography class, one example of a task might be, go take a picture. Go take a picture, thank you, of a building. And so you go out and you've got your camera and you find a building and you take a picture and you come back and you're like, is this good enough? And maybe I say, yep, you have a picture of a building, great job. Or maybe I say, yeah, you have a picture of a building, but it's a terrible picture because I know you know how to take pictures better than that, and the composition's all bad and it's out of focus or whatever, and you might go do that task again because you didn't do it well enough. But once you've completed the task with appropriate quality, you're done. And we will do stuff like that in this class. There are going to be times when you have a task to do and your job is to get it done. Much of the time, though, we're going to be practicing skills. Skills, and there's all sorts of analogies, are things that you you're not trying to cross off your list. I am done. I've accomplished it. Instead, it's something that you can continually improve. And I think really the best thing for you would be to think about what in your life outside of school or inside of school, what are the things that you really strive to get better at? I know some of you do sports, and you may do art, you may do music or theater, you may really love one of your classes, you might love this class, you might love a writing class. Those are things where if you really love what you're doing and you really want to get better, you don't think about it like, sweet, I'm done. Instead, every opportunity to increase your skill is there. And so I have lots of hobbies. I like to play music. I like to play basketball, and these are things that. So when I'm playing basketball with my kids, and I suck, by the way. Don't get me wrong. I'm not good at any of these things, but I like to do them. When I play basketball, even with my kids who are a lot younger than me and smaller than me, I am better than them because I'm bigger than they are. I still work on my skills when I do that because I like playing basketball so much. I'll work on something, like a little three-point set shot or free throws or driving for a layup or whatever. And as my kids get better and challenge me more, I have more fun playing and working on my skills. I get better, and I'm still not good, but it's super fun. And I would invite you to think about whatever it is that you consider your personal skills that you enjoy working on and developing, and think about what that looks like and what that feels like. I get that you may not love the work that we do in school or in this class in particular, but you can still sort of apply that approach. With a skill, you can always get better. It does not matter how good you are, you can always get better. No matter, even if you were the best in the school or in the state or in the world, there's always improvement to be made. And so it's kind of fun if you enjoy improving at things. It's kind of fun to think about, okay, well, what could I do to get a little bit better at something? When you are working on a skill, there's no point where you would say, I'm done. There are definitely times when you say, I'm good enough. You may, do some carpentry work, and there may be a point at which you're like, okay, well, I am good enough to put siding up on a house. I can do that now. So then you can accomplish a task. But that doesn't mean that you still can't get better, right? Even the best house siders could still get better. They could get faster or do a better job or make it more waterproof or something. This piece right here where it says your proficiency at a skill can often be measured by performing a task. That's a test. That's what tests look like, and we have them in a variety of arenas. In school, it's usually some sort of a paper and pencil thing. You're given a task to do. Based on your performance on that task, we try to determine what your skill is. I have given up on tests in my classes because I no longer think that tests tell me anything about your skill. I have students who do really well on tests that I don't think really understand the material. There's a variety of reasons that can happen, and I'm not accusing anybody of anything, but I've worked with students who are like, okay, here's my work, and they got it nailed, but if I ask them a question, they can't answer it. They don't know the material. They just figured out how to ace a test. And the opposite happens too. The opposite happens probably more often, where I have a student, I know they know what they're doing. They take a test and they don't do well. That sucks. Nobody wants that, okay? So we don't need to have that set up here. When I wanna see your proficiency, I am gonna observe you carrying out a task. So I wanna know how well you interpret motion graphs. So at some point I'm gonna have to ask you, interpret a motion graph so that I can see it. But it's not a test, it's not a formal sit by yourself and no cheating. It's I'm gonna watch you do this thing, and based on what I see, I'm gonna be able to evaluate whether you can do it or not. And it's the same kind of evaluation that you would make if you were hiring somebody to do something for you that you wanted done, whether it was putting siding on your house or detailing your car, right? If you if somebody's like, I'll detail your car, and then they get out the steel wool and the sandpaper, you're like, no, you won't. Like, you can tell the people who don't know what they're doing. If somebody goes to put siding on your house and like they pull the old siding off and there's like a huge hole in the sheathing where there's like termites pouring out, and they're like, we'll just cover this up. You know, they don't know what they're doing. So that's what we look for when we're looking for to evaluate proficiency with a task. If the questions you're asking yourself and me are along the lines of, how am I doing? Or what should I practice next? Or how do I do such and such? Or can I take a break? Those are the kinds of things that characterize sort of a skill-based mindset. If you ask yourself or ask me, can I take a break? That implies that when you come back, you're gonna keep practicing the skill. If you say, can I relax? That implies that there's a point at which you think you're done and you've accomplished whatever it is that you're going to accomplish. Can I relax is a task. Can I take a break is a skill. And I would say, like with the photography thing, and being a good photographer, being a photographer is an example of a skill. How many of you like photography? Anybody? I love it. I love taking pictures. And so if you were to tell me, go take a picture of a flower, I could do it. I could go out and take a picture. I think I could take a pretty good one. But if you were to tell me, hey, here's some things to think about when you take pictures of flowers. Here's ways you can improve your flower pictures. Go out and practice those skills. Then I wouldn't just take one picture. I would take a whole bunch and I would compare them. And when I came to you and asked you to help me evaluate how I was doing, I wouldn't say, am I done? Is this good enough? I would say, which of these looks best to you and why? And then I would try to figure out, well, what was my aperture setting for this one? How far away was I? Was I zoomed in more or less? Like, what did I do that created a picture that you like better? Maybe it was just the flower, right? Or maybe it was something that I did. Those are skills, and that's what I really would like to move all of us toward, okay? So I'm gonna pause here for just a second, keeping in mind that the camera is rolling. If anybody has any questions and you're comfortable asking, ask away. Does anybody have any questions about any of this? Okay, if you have questions and you're not comfortable saying it while the camera is on, no worries. Please let me know later. And I don't care how you let me know. You can send me an email, you can ask me in person, you can write a note and put it in my mailbox, whatever. Like, it's all good. I want to know. I want to answer any questions that you have, and I don't want to put you on the spot, especially with the camera on. So the next thing that I want to show you is related to all the work that we've been doing and are going to continue to do. And this is kind of characteristic of how we're going to approach material in this class. So what is typically going to happen, not always, but very typically, is I'm going to give you some time to play around with stuff. There'll be equipment to use, motion carts that roll around that measure their own position and velocity, springs and masses and all sorts of stuff that you can play around with, and I will kind of point you in a direction. And that's what these preliminary labs are going to look like. Explore and experiment, take some measurements, see what you can figure out on your own. And I'm going to ask you to practice some skills while you do that I have never showed you. So some of you like that kind of thing. That's how you roll, and so that works really well for you. Others of you need me to show you how this stuff works at some point. And so that's what'll happen. We'll have a couple of days to play around, then I'm going to show you stuff. Then you'll have more time to work and develop and practice those skills. All right. So today we're going to go through some of the skills, in particular these first two that have to do with interpreting motion graphs. This last skill right here, converting a position versus time to a velocity versus time and vice versa, we'll start that today, but we won't get all the way through it. We'll just get partway through it, and then I'm going to give you time to work on some of those skills. The work that you'll do today, some of it is going to be stuff that I'm showing you. Some of it is still going to be things that I haven't showed you yet, but you'll get it. You'll get it on Thursday. So what I want to start with is this idea of interpreting motion graphs. And we've really only looked at two. There's a third one that we'll get to know a little bit starting next week, which is an acceleration versus time graph. But the ones that you were playing around with the motion sensors were position and velocity versus time graph. So let's start with a position versus time graph. And the first thing to think about here is that for a whole bunch of reasons, we generally refer to an object's position along a single line. It's one-dimensional, for those of you who know that. We give it the variable x. X is our location variable. T is our time variable. And that's not super complicated, except that when you set it up on a graph and graph it such that position is a function of time, then what you end up with is your x-axis is t and your y-axis is x. And that's unfortunate because that's confusing. And it's even more confusing because by convention, if we're dealing with horizontal motion, we call it the x variable, right? That's something moving along a line, sort of left to right or whatever, we think of that as x. X represents your position along that line. But if we know something is moving up and down, then we often usually call it y. So sometimes the y-axis for position versus time graph is y, and sometimes it's x. When we start thinking about two-dimensional motion, one single object will have both a horizontal and a vertical position. So we'll have an x versus t and a y versus t, two graphs for the same object. One of those will have x for the y-axis, the other will have y for the y-axis. And it gets confusing pretty quickly. So just keep in mind that you are going to need to keep careful track in your brain of these things. And I'll try to speak really clearly when I refer to these things, talk about the x variable and the y-axis, and make sure that you know whether I'm talking about position or one of the axes on a graph, because the letters don't match up the way that we sort of wish that they would. And not universally, but typically, at least in this class, we're going to be measuring our position in meters. We'll be measuring our time in seconds. So it's always good to put units on things. For a graph like this, we're going to be thinking about it qualitatively. We're not going to need to have any numbers on here. We don't need any numbers to be able to think about an object's relative motion, its relative location, like is it further away from a certain place than it was before, which direction is it moving faster or slower? We can figure all that stuff out without putting any units on here at all. So I'm going to leave them off to start with. And this is from the preliminary lab. This was in there. These were the things that I was asking you in general to sort of give you a chance to think about those skills of interpreting a graph. The first one says, what does the slope of a position versus time graph look like when you're moving slowly versus moving quickly? And this is fun right off the bat because here's a line right there. Does that look like fast or slow motion to you? Anybody have a guess? Who doesn't mind having their voice show up on?
Slow.
Yeah, and so because it's not very steep, so we want this to be slow. And here's the thing. What is the definition of slow? Like if I tell you that I'm moving at 30 miles per hour, is that fast or slow?
Slow in the car. Well,
Is it slow? It depends, doesn't it? If I'm in a car, not so fast. If I'm in a jet, you're not even off the ground. But if I'm in a little red wagon being pulled by a 7-year-old, that's fast, right? And so these are relative terms. So all we can say here is that it's not that this is slow, it's just that it is slower than, say, this. So if we have a steep slope, it's fast. If we have a shallow slope, it's slow. But it's not really slow, it's slower. And it's not really fast, it's faster. Compared to each other, these are relative speeds, right? The steeper the slope, the faster the speed. Is it fast? You would need to know what's moving and what the units are, right? So there's no universally accepted number that makes a speed fast. Fast for a baseball is very different from fast for a wiffle ball. All right, so the steepness of the slope tells you the speed of your motion. What about positive, negative, and zero slopes? Here are two sections where there's a positive slope. Here's a section here where there's a zero slope. And here's a section where there's a negative slope. What is the difference between these three sections? This section is positive, this section is zero, this section is negative. What would we see? What do those slopes tell us? Yeah.
You'd be going away from the point, then stopping, then going towards the point.
Right, so basically, the sign of the slope is an indication of direction. If the slope is zero, then our object isn't moving, it's motionless. If our slope is positive, then we're moving in one direction. If our slope is negative, then we're moving in the other direction. And this gets a little bit interesting too, for a couple of reasons. One is that so far, we've mostly been focused on trying to work with these sensors. And these sensors, come on in. Yeah, no worries. Don't worry about it, it's all good. These sensors have some limitations. One of those limitations is they will only detect the position of something that is being faced by the little shiny circle. So if you're not like visible to this thing, your position doesn't get registered. Do you have a position? Yeah, I'm somewhere, right? It doesn't matter, this sensor isn't even plugged in, but I'm still somewhere. So when we look at these graphs, we have to make sure that we recognize that, like, well, if we make a graph with a motion sensor, there's going to be limitations. But if I look at this graph right here, there's no rule that says this graph had to have been made by a motion sensor. This has to reflect the motion of an object that's being tracked by a motion sensor that has the limitations that this one does. You all know about like air tags and stuff like that. Those are location sensors. Those can tell you where anything is at any time. Like, you don't need this, and it can tell you just where you are. It uses a totally different system, but you don't need this to have a position. So what that means is a couple of things. The first is we can have a negative position. With the motion sensors, that would not be data that it could record, right? But it's absolutely possible for something to move past our position zero, whatever that is, and continue. So if I am walking toward this motion sensor and I just keep walking, right, I'm now in a position that the motion sensor would record as negative. It can't record it because it doesn't work that way, but you all could. We could all agree that if I am right now standing at +1, +1 meter location, that now I'm standing at -1 meter location. We could agree. The sensor wouldn't show that. If we were using a computer and a graph, what would happen is it would start to glitch out right about here because it doesn't work very well for super close distances. And then as I moved away from it, it would be measuring like how far away the wall is. It wouldn't be giving us any meaningful data. But my position relative to this sensor is easy for us to see. So this is perfectly valid information. Where is position 0? We'll talk about that next week, but it's really like wherever you want it to be. Sometimes somebody else makes the decision. This sensor has it built in position 0, which is the shiny part. That is position 0 with the sensor. But if we were to go outside and go to the track, we could take a rock and put it down and say, this is position 0, and measure everything relative to that position. Positive would be one way, negative would be the other way. Is there any reason to say that positive is left or right or up or down or towards us or away from us? Not necessarily. We just need two directions. And one of them is going to be positive, one of them is going to be negative. The next section says, what does it mean when the slope is changing on a position versus time graph? So that would be something like this. What does it mean when instead of a horizontal line or a diagonal line, we have a line that is curved? And this one looks like it starts off with a negative slope and then it curves and becomes at least close to horizontal. What does that tell you? Yeah.
You're like accelerating or decelerating?
It tells you that's right. And what acceleration or deceleration means is that your velocity is changing. With these graphs, this is always going to indicate a change in speed. Okay, so a line with a constant slope is going to mean a constant speed. On a position versus time graph, when you see a curve like this, that's a change in speed. Steeper slopes mean faster, slower slopes, or shallower slopes mean slower. So what that means is we are starting here at a relatively steep slope, transitioning to a shallow slope. That's slowing down. This would be slowing down as well. We started off steep, we ended up shallow. A speeding up curve would look like this. We're starting off pretty shallow and getting steeper and steeper and steeper. Or this is a speeding up curve as well. So on a position versus time graph, we can see speeding up or slowing down. If the slope is getting more shallow, it's slowing down. If the slope is getting steeper, it's speeding up. And then the last thing here has to do with the coordinates of a point. And this is easy to show, it's a little hard to say in words. So basically what I mean is like this graph consists of a bunch of points that are infinitely close together, right? So this point right here would be a pair, right? And this would be a pair of coordinates. The first coordinate would be our x-axis, which is t. The second coordinate would be our y-axis, which is position, or x. This point right here tells us two pieces of information. Those pieces of information are the time of a measurement and the location or position of whatever object it is that we're measuring. Was this a sensor? Maybe. It might have been this motion sensor, but it also might have been us out on the track, or it might have been a car driving down the road, or it might have been anything that was moving. At some time, it had this position. And what that kind of leads you to, so that information can be useful. Like you might need to know in this class or in life in general, where was something at a certain time, right? And so that's what this information will give you. What's more interesting is when you start to think about it, well, so if position is a function of time, then if we kind of move our finger along the time axis and think about how our position is changing, we can tell the story of motion, right? Here we have an object that's located at a positive position. I don't know what it is, but I know it's on the positive side of our 0, wherever that is. As time goes by, it's moving and its position is becoming more and more positive. And now it's moving faster, got a steeper slope, it's moving farther in a certain amount of time. And now it's as far away as it's gonna get, and it's not moving. And then it starts moving the other direction. Towards the sensor? Well, if this were a sensor, then yeah, this is moving toward the sensor until it gets to here. But as it continues moving in that same direction, now it's moving away from the sensor. And again, there might not be a sensor, right? This might be you walking towards the rock on the track and you just walk past it. Now you're in positions that would be negative, and now your position is becoming more and more negative, but it's not happening as quickly. And now you're standing still. So you take your finger and you kind of move it along the graph and tell the story of how an object is moving over time, right? So that's what interpreting a position versus time graph looks like. Does anybody have any questions about that? Okay. The next one has to do with a velocity versus time graph. Velocity versus time graphs are a little bit more complicated, and the reason for that is because our brains in general have been trained to use a graph like this to show us where something is. We just, up until now, most of you have not spent a ton of time thinking about the speed and direction of an object's motion as it is reflected on a graph that shows velocity as a function of time. So it's gonna be a new thing, all right? So what does it look like? What does motion look like with a perfectly horizontal slope? If we have motion like this, what would that look like? What would we see? If an object were moving with, and this were its velocity versus time graph. Any ideas what this looks like? Bastian?
That looks like just moving at a constant speed.
Right, okay, so we have the idea of constant, right? This section right here would be reflective of a constant speed. As time goes by, your speed doesn't change.
Yep.
You're not standing still, you're moving, you're just not speeding up or slowing down. What about this section right here? That also has a horizontal slope. What's happening here? Did you go back? You just went back to where you started, right? What do you think? Back to where you started? What? Yeah. So this is where, with a position versus time graph, 0 means a place. With a velocity versus time graph, this 0 is your speed. It's not that you moved somewhere different, it's that you stopped moving. Here, you're not moving at all. What about something like this? Or this? Here we have an angled line, right? It's a diagonal. And here we have a curved line. The slope is changing. What information is there? Forget about the fact that it's below the x-axis for a second. What does this straight line tell you about an object's motion? What does that look like? Yeah?
Motion is increasing.
Something is increasing. It's you're not, I'm not saying you're wrong, but there's a vocabulary thing there,
It's
yeah.
moving faster at a constant acceleration.
Yeah, it's moving faster. So, and we'll get into like, well, how do we tell if it's moving faster or slower? In this case, it's moving faster. And its speed is changing at a constant rate. That's what gives this line a constant slope. As time goes by, its speed kind of ticks up at the same rate. What about this? This is what? Any ideas? Philip?
Deceleration,
Deceleration? What does deceleration mean?
slowing down.
Slowing down, right? That's what we want this to be, Ryan.
You reach a plateau of speed and just
You
keep
reach a
doing it.
plateau of speed. That's not the same as slowing down, is it? Yeah, when we see this, our brains want this to be slowing down. This looks so much like what we would expect slowing down to look like. But if you think about what the information on this graph is telling us, your speed is becoming more and more and more and more negative. Here, it's still becoming more and more negative. Here, it's not slowing down, it's maintaining a constant speed. That's what these horizontal lines mean. So this section right here, it's not slowing down. We need another way to talk about this. It's not that it's slowing down, it's that the rate of change is slowing down. It's speeding up, but it's speeding up less and less and less fast until it stops speeding up. That's what's going on here. And yeah, acceleration is the term that we use to refer to the rate of change of velocity. We'll talk more about that next week. Yeah.
And what is negative velocity exactly?
Yeah, so let's talk about that because that's the next piece here. So let me just add that real quick. So this is a changing speed, and this is right here the rate of change is changing. And that's a weird thing to talk about because that's like, well, you're not slowing down. but your speeding up is slowing down. Your speeding up is happening less and less quickly. Okay, and then the next piece here, what do positive and negative and zero slopes? Well, we figured out zero already. Zero means your speed isn't changing. If you're moving, you move at a constant speed, there's a zero slope. If you're not moving, you just persist in not moving. But positive, negative slope means something. A positive slope means that your speed is increasing in the positive direction. And we're gonna talk more, so I'm gonna defer like a detailed analysis of that until next week, because we still need to like define some terms and talk about like what does zero mean, what does slowing down mean, what does towards zero mean. We got some stuff that we need to iron out. But essentially, what these positive or negative slopes tell you is whether your speed is becoming more positive or more negative. That's really the limit of what we can say by knowing the slope. Now, in this case, we have a little bit more information. This is a negative slope, and we know that the speed was zero at the start. If your speed is zero, and then it gets more and more and more negative, then you're speeding up. You have to be. If you're moving in the negative direction, then you're gonna have a negative velocity. Negative velocity isn't something special, it's just what direction, right? If you have a negative velocity, you're going one way. If you have a positive velocity, you're moving the other way. If I were to use this little setup, this is my position zero, it's not a sensor, it's just a marker. If I say this is my positive direction and this is my negative direction, then 1 meter per second positive looks like this, and 1 meter per second negative looks like this. Same speed, different direction. I just walked by the sensor. I'm still moving in the negative direction now. The negative direction is this way. And I'm all the way over here now, and I can move toward the sensor in the positive direction. Still toward the sensor in the positive direction. Positive toward the sensor. Now I'm moving away from the sensor, still in the positive direction. So we can move toward or away from our 0 point without changing direction if we walk past it. So that, we have to iron all that stuff out, and we'll work on that next week. The last piece is this piece. We did this with the position versus time graph. This is the idea that if we look at a certain point that makes up any one of the infinite points on this graph, we can look at the coordinates. In this case, maybe that's 7 seconds and a negative 0.2 meters per second. We don't know because we don't have units on here, but the first coordinate is going to tell us the time of a measurement. The second coordinate is going to tell us the speed and the direction of whatever it is that we're looking at that time. That means we can talk about this object's motion the same way that we talked about a position versus time graph. Only what we're saying isn't where the object is, but how fast it's going and what direction. So we can start here. At this time, the object is moving at a constant speed in the positive direction. So let's say positive is this way now, just because we can. So it's just moving, 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 and then it stops. And it stays motionless as some time goes by. And then it starts moving in the negative direction, slowly at first, and then faster and faster and faster and faster, and then it continues to speed up, but it doesn't speed up as quickly, and eventually it's moving at a constant speed. I can't show you that because I can't keep moving and point at this thing at the same time. Like, I ran out of room, right? But the position of this object is somewhat predictable. We know it's going to be moving this way for a while at a constant speed, and then it's going to stop, it's just going to stay put. Then it's going to start moving back, slowly at first, speed up, speed up, speed up, speed up, speed up, speed up, but speeding up slower, and now constant speed. Eventually it's going to go past its original position and keep going, right? If this just extends on, we don't know what happens, but it might just keep moving at a constant speed this way. So that would be like you throw a boomerang, and it goes off this way for a while, and then it stops and it hovers for a little bit, and then it slowly starts to come back, and then it speeds up and goes faster and faster until it sort of hits a maximum speed, and it just keeps going. That's what that would look like. So those are skills that want you all to be able to do. And what I want to show you next, so there's a couple of things that I'm going to defer to Thursday. So this is one of them. The first thing is we're going to work on this on Thursday a little bit, and basically this is like a graphic organizer for interpreting these motion graphs. We can think about the motion graphs in terms of what does a single point tell us, and what does the trend tell us? The trend is the slope of a line or a curve, the positive or negativeness of it, the steepness of it, right? And we can think about that for a position versus time graph or a velocity versus time graph. We're going to think about it very superficially for acceleration versus time as well, but not yet, okay? But we'll hit this on Thursday. We'll come back to this on Thursday. And what I want to show you today is a skill that I think some of you probably made a little bit of progress on in the Match This Motion preliminary lab, but most of you didn't get here, or if you did get here, you weren't quite sure how to go about doing it. So I'm going to show you how to do it. And basically what we can do is, if we think about the fact that a position versus time graph tells us something about how fast something is moving and in what direction, steeper slopes mean increasing speed. So we have an idea of whether something is going slower or faster by the steepness of the slope. And the sign of the slope tells us direction. Positive slopes are moving one way, negative slopes are moving the other way. We could use that to create a velocity versus time graph. If we know how fast something is going and we know what direction it's going, then we can talk about how its velocity looks over time. So I'm going to walk you through an algorithm. An algorithm is a system, a series of steps for accomplishing a task. Here's the algorithm that I use to create a velocity versus time graph from a position versus time graph. The first thing that I do is I look at my position versus time graph and I break it into chunks that all have the same slope. So when I look at this position versus time graph, I see that for the first, you may not be able to read these units, and that's okay. This is 2 seconds here. For the first 2 seconds, I have a constant slope here. For the next 2 seconds, I have a constant slope here. For the next, this is 1.5 seconds. I have a constant slope. And then there's a half second here where there's a constant slope. There's 2 seconds here of a constant slope. This is 1 second with a constant slope. And then 2 seconds with a constant slope, right? And those are all like, we can think of those each as being like line segments. They're straight lines, constant slope, and we can find the slope because we know how to do that. It's rise over run. For the flat sections, the rise is 0. So we know, like, rise over run is 0. If your rise is 0, doesn't matter how much time you're there, you have a slope of 0. So for the first 2 seconds, we have a slope of 0. From second 4 to 5.5, we have a slope of 0. From second 6 to second 8, we have a slope of 0. The rest of these time periods, it's not a 0 slope. For times 2 to 4, it drops down by 10, and again, you may not be able to read this, but this is 0, 5, and 10 meters. So it goes from 10 to 0. That is a rise of -10. That happens over 2 seconds, so that is a slope of -5. From 5.5 to 6 seconds, I'm going from position 0 to position -15. That's a rise of -15. -15 divided by 1/2, which is the run, is -30. So the slope here for this section is -30.